What's up, everyone? It's Mr. Park here. We're going to be talking about total internal reflection, something called critical angle. It's going to be an application of what we've been learning about in the unit of refraction so far. It's going to be pretty interesting, so just hang on to your seats. Okay, so as we've been learning in refraction, that when a light, let's say this is a denser material into a lighter material, as light, an incident light ray comes in at a certain angle, we'll call that theta I. It's going to refract coming out of the material at an angle away from the normal line, and we will call this theta R for the angle of refraction. Now, what we want to investigate today is there an incident angle large enough to where, hold on, let me use a different color for this, where theoretically, if you have a large enough angle of incidence, that angle of refraction is going to keep getting bigger and bigger and bigger until maybe at one point we're going to get some sort of refraction right along this line here, and that angle is going to be 90 degrees. What happens then? Well, it turns out a lot of critical things happen then, and we're going to call that the critical angle. So we will denote this theoretical angle theta C for critical, because at theta C, what ends up happening is that angle of refraction gets to be 90 degrees. So what happens then? What ends up happening is actually, if you exceed that critical angle of incidence, even by just a little bit, so let's say this red arrow is a new light ray coming in at an angle greater than the critical angle, then you won't get refraction at all, actually. It won't bend out, it won't even go across the surface like we saw here at the critical angle. But if you exceed it by just a little bit, you get something called total internal reflection, where that light ray actually bounces back into the medium that it came from. Pretty interesting, right? So we actually have a definition for this critical angle. We say that the critical angle and we denote that with theta C for critical, is the smallest angle of incidence where total internal reflection occurs. So you should be able to find that in your total internal total internal reflection notes, guided notes on your Schoology. It should be there. We also have some math to do as well. Actually, before we go into an example, let's see if we can find some generic formula for the critical angle using this Snell's law. So let's say, or we had before, that N1, and let's call this sine of theta C, because that's what we're interested in, is equal to some sort of angle here. But remember, if we wanted to refract, that critical angle here is when that refracted angle was 90 degrees. So we want this refracted ray to be 90 degrees. So we have sine of 90 degrees as your theta 2. Now what happens here is that simplifies out to N1 sine of theta C is equal to N2 sine of 90, if we plug it into our calculator, or if you have any other ways of doing it, is actually equal to 1. Pretty nice, right? Wow, beautiful math. So easy. And if we simplify this out further, we get, oh my goodness, we get sine of theta C is equal to, and we're going to divide both sides by N1, and we get, let me rewrite that here. If we divide both sides by N1, that's an ugly N, we get sine of theta C is equal to n2 over n1. Now, if you remember, to get rid of this sign and to isolate this thing, we're going to take the inverse sine. So the inverse sine of sine of theta c is equal to the inverse sine of n2 over n1. And when you take the inverse sine of a sine of something, all you get left is the angle of critical angle. I keep wanting to say the angle of criticality, or like, because it's the angle of refraction and angle of incidence, but it's critical angle. So my apologies. But anyways, so we get a generic formula for that critical angle, which is the inverse sine of n2 over n1, depending on your media, different indices of refraction. Cool? Cool. Let's do an example. For the example, let's say we have diamond. Let's say we have diamond here and air up here. And for air, we know that the index of refraction is 1. But for diamond, we have an index of refraction of 2.42. So let's try to find that critical angle of diamond, where if you shoot a ray of light from inside of the diamond, at what angle is it going to reflect back? So what is that critical angle? Put a little question mark here because we don't know yet. So let's find that out. Now, I know I gave you a generic formula for the critical angle, but you know what? For fun, or not for fun, but for good practice, let's just try to derive it ourselves from Snell's law originally. So we had, right on this side actually. So we had n1 sine theta of 1 is equal to n2 sine theta of 2. We know that n1 in this case is actually diamond. So n1 is the n of diamond. Mark that with a D. And the sign that we're looking for is that critical angle instead of 1. And here we have n of air times the sign of, we're looking for, well, this is what's going to end up happening, but we're looking for what that angle, I'm doing it again, that critical angle, where that's going to be, it's going to shoot out this way, because any bigger than that, it's going to reflect back in. So we're looking for that breaking point. So we have 90 degrees. So let's do a little bit of math magic here. So we have substitution, 2.42 times the sine of theta c is equal to, if we substitute in the index of refraction for air, beautiful, it's 1 times, as we said earlier, the sine of 90 is also 1, and 1 times 1 is equal to 1. Oh, let's move this down here. We get, so we get 2.42 times the sine of theta c is equal to 1. Great, beautiful. Now we're going to divide both sides by the 2.42 to get rid of the 2.42 on that side and isolate the variable that we want, and we end up getting the sine of theta c is equal to, these cancel out, 1 over 2.42. Great. How do we do that? How do we get rid of this? Oh, well, like I said earlier, we're going to take the inverse sine of sine of theta c of both sides. So we get 1 over 2.42. Let me see if I can show you my calculator. See what we end up getting. I am so sorry, my camera keeps fading to the left. But anyways, that's where we left off. I'm going to show you how to find that on a calculator. Shoop. And we have the second sine. So we get the inverse sine of 1 divided by, what was it? 2.42. Oh, that's not a 2. 2.42. And that should give us 24.4. Alright, so let's put that in there. So we get theta c is equal to 24.4 4 degrees. And that, my friends, is your critical angle for diamond in air.